Good evening, students. Welcome to the session. Welcome to Unacademy YouTube classes. This is a VV live class, and this session is going to discuss on nuclei. So to get a plus subscription, okay, I recommend better to use for this code VV live, right? So due to this plus subscription, you are having many benefits like you see here, premium content at affordable price, structured live classes, and also dedicated live doubt clearing sessions will be conducted regularly. Quizzes at regular intervals for self-analysis, batches for complete preparation of your course, test series for daily practice papers, full length mocks, etc. with detailed analysis. This all you are going to get under single plus subscription. If you are using this code VV Live, you are going to get it. And also, students, here you see in this Academy plus subscriber, okay, that category you are going to get 20 plus top educators, 10 plus batches, 250 courses, 2000 plus lessons, and many more. Every day it's going to add. So I request you and I suggest you use the best. You have to use the best use of this Academy plus classes. And today, as we discussed before, today our part is we have to discuss on nuclei. Okay, nuclei is going to be discussed. Part 1. Are you ready, students? Hope you are all ready. Okay. Now you see. Nuclei. Nuclei means it's the discussion about nucleus of an atom. Nucleus is the singular, whereas the nuclei is the plural, right? So as we know, molecules are made of atoms. Inside an atom, nucleus is present. Say here is the molecule, for example. Inside the molecule, what are present? Atoms are present. Even inside that atoms, nucleus is present. So as we know that nucleus is the central part of an atom. See here, suppose if it is one molecule, for example, you see for this structure, this is matter. This matter is made of molecules, different molecules it has in it, right? Inside molecule, what are present? Atoms are present. So let me write for this, molecules, right? Made of atoms, right? In this atoms, nucleus is present. Inside the nucleus, what is present? Inside the nucleus, what is present? Nucleons are present. See for this is the nucleus, right? Inside the nucleus, what are present? Protons and neutrons. Be remember for this. Inside the nucleus, protons and neutrons are present. So therefore here, these are said to be nucleons. These are said to be nucleons, right? Now, surrounding to this nucleus, what is the leftover one? What are the fundamental particles are moving? Suppose if it is the atom boundary, right? Inside this an atom, between this nucleus and circumference of this atom, okay, there are electrons revolution around this nucleus. You know that also. Okay. Now you see this one. Whenever surrounding to this nucleus, right? These electrons are revolving. There is an electrostatic force between this protons and electrons. So electrostatic attraction. Electrostatic attraction is there, right? Since unlike charges, these are unlike charges. One is electron, The second one is proton. These are unlike. One is having negative charge, one is having positive charge. Unlike charges has to attract. According to modern theory of electrification, unlike charges has to attract. See students, here actually our area is nucleus. Inside nucleus, nucleons are there, right? So about that we have to discuss. And coming to here, I can say, while I am discussing about nucleus, first I will say nuclear properties. What are the properties it is having? Nucleus is like this, right? Inside protons and neutrons, we are saying protons and neutrons are there. Properties. For that, if you are asking me, I can say in that radius is one factor, and the next one is the density. These are the primary things and very important things for which we have to know about nucleus. So radius and density. You see here, okay, for visualization it seems to be in spherical shape. So nucleus assumed to be in spherical shape. Spherical shape. This is the first point. Okay. So it is in spherical shape. So that's why, therefore, we can write for radius and even density also, right? Coming to this radius, here radius of any nucleus. See, it is the center of the nucleus, like that you treat. Till where this radius can be taken, for that there is no there is no exact calculation, exact measurement we don't have. Where it's going to end, nucleus, where nucleus radius, where it is going to end in an atom, for that there is no sharp edge, means for nuclear radius there is no sharp edge. So that radius, okay, if I denote with this capital R, that radius is directly proportional to a power 1 by 3, this relation we have. You can ask, what is A, sir? A means what? You say this chemical element representation, any chemical element can be represented in this way, X, Z, A, where here Z is nothing but protons number, this is nothing but protons number, whereas A is nothing but mass number. A is nothing but mass number. You see here, students, mass number means, A means number of protons plus number of neutrons. So this implies number of neutrons as A minus Z. Suppose if I write helium-24, for example, I am writing for this. For this case, if you are asking me, protons number is 2, right? Whereas mass number is 4, right? Whereas coming to neutrons number, it's A minus Z. So that's why 4 minus 2, which gives 2. So it has 2 protons, 2 neutrons, totally mass number is 4. Like that, isn't it? Now you can see for this example, suppose uranium 92-235 is there, for example. In this, protons number is 92, okay, mass number is 235, right? And whereas neutrons number is 235 minus 92. So that's the neutrons number. So likewise, we have to find out the protons number and neutrons number. For example, this nucleus is shown like this. The radius is shown up to here. For example, you see, just for a glance, if you see, helium-24 I am taking, helium nucleus as we know. In this just now we written, it has 2 protons. This is the protons number. It is having the neutrons number 4 minus 2. So 2 neutrons it has. So how many neutrons it is having? So 2 neutrons it has. For that also, let me write, it is having 2 neutrons, right? So now up to here, okay, up to here this radius can be chosen here. But in case of some other elements like heavy elements, suppose if I say heavy elements means, for example, just now what we have taken, uranium 92-235, for example, if I take for this, how many protons are there, students, here? Here how many are there protons? Protons number is 92. So protons P like that 92 we should add. So this radius can be extended. Which means radius depends on mass number. So as this protons number and even neutrons number also. Neutrons you should show here in this nucleus. Within the nucleus boundary. So for that it can be increased. So that time what I can say, nuclear radius will will increase, depends on mass number. So therefore, how it is related? R directly proportional to A power 1 by 3. With this relation, we have the relation between mass number and radius. Students, you see here, radius of any nucleus. Radius of any nucleus, you take hydrogen, you take helium, you take carbon, you take nitrogen, whatever it may be uranium, thorium, whatever may be the element. Students, what you have to know is radius always directly proportional to A power 1 by 3. R is directly proportional to A power 1 by 3, isn't it? So likewise, radius is depending and can be written like this. R is equals to, if I write equality symbol, this proportionality symbol can be taken out and I should write for one constant, which is nothing but R naught, A power 1 by 3 as it is we are writing. So whereas R naught value is not a fixed one again. R naught is having the value from 1.1 Fermi to 1.4 Fermi. As we know, 1 Fermi is nothing but 10 power minus 15 meters, students. Very short distance. See here, this is the atom. See here is the nucleus, like that, just imagine. So atomic radius is in the order of 10 power minus 10 meters, which means 1 angstrom. Whereas nucleus radius, this nucleus radius is in the order of 10 power minus 15 meters only, which means 1 Fermi. Should know this is the average radius of the nucleus. I'm sorry. So likewise, you see how far this radius is smaller than this atomic radius. Atomic radius. This is the atomic radius. This is the nucleus radius order, right? Likewise, here we can take this relation is very important, students, while solving the problems. Any type of examination, competitive examinations, you're writing. This formula is well used, very useful equation, this one. And next, coming to students, we are going to discuss about the density of the nucleus. You see here, nucleus is present like this. Just imagine, nucleus is present like this. It is in this way. So density, if I ask, generally density is nothing but mass by volume. How much mass it is having? In this number of protons, suppose P like that I am writing. Number of neutrons, N. I don't know number of neutrons and I don't know number of protons here in this particular. But for I don't know means how many protons and neutrons are present in this nucleus. For those all the nucleus we should add. We should add the masses of all the nucleons. For that, what I am going to say here is total mass of the nucleus means total number of nucleons, which means mass number. This is A, mass number, into mass of each nucleon. You can ask, what is the mass of your nucleon, sir? Here we have proton and a neutron. So does proton mass and neutrons are equal? No, not exactly. With slight difference, mass of neutron is greater. For that I will explain anyhow. Just after this step, you see for this first. So mass number into mass of each nucleon whole divides by volume. Volume is to be written. Volume of this body. This body means nucleus. This is in spherical shape. So nucleus is in spherical shape. So volume of a spherical body can be written as 4 by 3 pi r cube, isn't it? 4 by 3 pi r cube. Now come to the point again. Now you see here density we are going to find mass number into mass of each nucleon whole divides by 4 by 3. 4 can be written here, 3 comes to numerator, pi. R means what? Student, you see, R means radius of the nucleus. Here this is one of the important relation. So R is nothing but R naught into A power 1 by 3. So that I am writing here. R naught into A power 1 by 3. It is to be cubed here. You see here in the step, R cube is there. So it is to be cubed. So like this density should come. So now finally what I can write is D is nothing but 3 into, here you see A is there now, here in the denominator, A power 1 by 3 whole cube is there. Means A power 3 by 3. So 3 gets cancelled and thereby A also gets cancelled. So 3m by 4 pi, right? R naught cube. So now students, here you see, here m means mass of each nuclei, for which we should take, you see, mass of proton is taken like this, 1.672 into 10 power minus 27 kg, whereas mass of neutron is 1.675 into 10 power minus 27 kg. You can observe clearly the difference in this third decimal point here, right? So 672 is here, 675 is here. So I can say mass of neutron is slightly greater than mass of proton. So by the time while you are writing this mass for nucleon, you may get it out for which we should take mass, whether for proton or neutron. Usually in problems they will give mass of each nucleon as 1.6 into 10 power minus 27 kg in order to avoid this little confusion. So you can apply, you can substitute for that value and you can show your final result. So 3 into 1.6 into 10 power minus 27 whole divides by 4 into pi means 22 by 7 or 3.14, whatever it is. So R naught value, so the minimum value I am considering 1.1 into 10 power minus 15, minus 15 meters. If I take, it comes in this way, 1.45, 3 into 10 power 17 kg per meter cube. This is the one of the important conclusion. Here you have to see for this. Here you see what is the order of the density of the nucleus, 10 power 17 kg per meter cube. That which is not possible for our imagination. 10 power 17 kg mass is accumulated per meter cube. Means about those three directions. Per meter cube means about x direction, y direction and z direction. Just imagine here one sphere. Just imagine for one sphere. In this direction, in this direction, in this direction. 10 power 17 kg per meter cube mass is accumulating. So it is a very dense region. What I can say is nucleus is the dense in the universe, dense region. So that more than this 10 power 17 kg per meter cube density in this universe, nothing is having. So any nucleus you take, this much of density it has. And also one observation is, whenever we are saying that equation for density as d is equals to 3m by 4 pi r naught cube, here there is no term a, mass number is not there. So that's why density do not depends on mass number. Here you can see clearly what happened here. A term gets cancelled here. So density do not depends on mass number. So for that what we can say is density for hydrogen is equals to density for helium. It is equals to density of the nucleus. What I am saying is density of the nucleus, density of the carbon. Likewise, even for uranium also, density is a constant. Density of the nucleus is equals to constant. How much it is? It is in the order of 10 power 17 kg per meter cube. This you should remember forever. So likewise, density of the nucleus is it is having density of the nucleus is having like that. So students, here you see, coming to the properties, what we discussed, very basic things, the radius, how it is related, on what factors it is depending, depending only on mass number. It depends only on mass number, nothing else, only on this mass number. Does this one density depends on mass number? No. On which it is depending? Nothing. Like mass number, radius, nothing that decides the density. It's a fixed, it's a constant, right? So likewise, what we are confirming here, So density of the nucleus, density of any nucleus, density of the any nucleus, what I can say is any nucleus is a constant. And how much order? It is in the order of 10 power 17 kg per meter cube. So very dense part in the universe. That also we have to note, right? And students, here now what I am going to say is in this, whenever these nucleons are present in this nucleus, nucleons I am saying, what are those nucleons? Protons and neutrons, right? This is very small dense region. This nucleus seems to be like this, but actually inside the atom, then how it looks like, you just see here like this. If you take one atom, okay, at the central part a small dot you put, that is the size of the nucleus. Actually Faraday told that, okay, Faraday told that if we construct a 10 cinema theaters lens as the radius, okay, there are 10 cinema theaters we are going to take, and the lens we are going to add one after another. So we should take that as the radius. Now construct one circle. Now at the center point you put one ink dot. That ink dot size is the size of the nucleus. So the circumference, whatever the circle you are going to draw, that is the nuclear radius, average radius. That much to that much this nuclear radius is existed. Okay, sorry, not nuclear radius, atomic radius. Atomic radius is existed till that circumference, whereas nucleus is present at the central spot. That central spot is nucleus. Students, once again I am repeating, 10 cinema theaters lens, one by one if you construct means one by one if you take, add up all those, and okay, you prepare for one a radius from that point, and you construct for one circle, and now at the central part you put one ink dot. So that ink dot size is the nucleus. So this becomes the radius of the atom. This radius radius is in the order of angstroms. 10 power minus 10 means 1 angstrom. Whereas this one, nucleus, is nothing but 10 power minus 15 meters, which means 1 Fermi. Right? So likewise, now what I am going to convey here is, for visualization we are drawing like this nucleus, but actually it is not in that size. In that small size, all these nucleons, n number means, suppose helium, if you are saying 2 protons and 2 neutrons are there, right? Suppose you are saying for calcium, suppose calcium 2040 is there, okay, so 2040, 20 protons it has, 20 neutrons it has in it, so 20 it should accumulate within this circumference. It is not possible. So for that, what you have to do, you have to go for construction of big circle now, big sphere, not circle, sphere. So in that sphere, 20 protons you have to show, and also 20 neutrons likewise. So likewise, what is happening? Automatically this radius is going to be increasing. So now my point is, how these nucleons can takes place inside the nucleus. You see, suppose if you throw one ball upwards from the ground, okay, you are throwing one ball vertically upwards. What is happening in that case? It is going up and again coming back. Means here, so in that case, what is happening? From the ground, if you throw any object vertically upwards, if you are throwing any object, it moves up and again it comes back. What is happening in this case? This body try to get a zero potential energy. Means here, okay, this ground is pulling this object. This ground is pulling this object towards its center. So some force is there, that is called gravitational force. Between this object and this earth. Earth is also again object. Say this as earth. So between earth and this object, say whose mass is small m, here is capital M, there is a gravitational force according to gmm by r square, as we know that. Now, how the force is existed between a small body and the earth? Likewise, there is a force of attraction between the nucleons, well inside the nucleus. Inside the nucleus, okay, protons are there, and also what we have? We have that neutrons. What we can see? Neutrons also. There's a force of attraction between proton to proton, neutron to neutron, and also neutron to proton, proton to neutron. So like this, all these are called, okay, attractive forces. We remember for this. All these are attractive forces, and are also these are strongest. These are so strongest superlative degree, strongest force. Okay, strongest forces. These are the strongest forces. So among the fundamental forces, we have fundamental forces, students. Okay, what are the fundamental forces we have in our nature? Fundamental forces. What we have? One is gravitational force, second is electromagnetic force, third is van der Waals force. The force is, okay, nuclear force, strong nuclear force. So this is the case of strong nuclear force. Means strong nuclear forces are existed between, okay, strong nuclear force are existed between proton to proton, neutron to neutron, and neutron to proton, and even proton to neutron also. So likewise, these forces are existed, and that's why they can able to retain in that nucleus. And also you see here, students, in order to combine those nucleus, some energy is required. Some energy is required, isn't it? Like how gravitational potential energy is used to hold the objects on the surface of the earth. Likewise, here some energy is required. You see, students, here, right, in this nucleus, okay, like 2 protons and of course 2 neutrons are present, right? About energies, if you are asking me, what I can say is energy of okay, individually all of these nuclear energies you take. Suppose proton energy, one proton energy, likewise one more proton means how many protons? 2 protons. 2 protons energies you add, likewise a neutron and a neutron means 2 neutrons. So 2 into each neutron energy, 2 into each proton energy individually you are adding, and you are going to get some energy you are going to get. And now secondly, this is the first case where you are going to weigh the masses of all the nucleons individually. So this is called what I can say is this is the theoretical mass. Theoretical mass. Theoretical mass is like this. Individually you are adding all the masses of the nucleons. So therefore, next after this, what we have to do is as a whole nucleus mass we are going to take. As a whole means in this 2 protons are there, 2 nucleons are there. As a whole, if you are adding, that is there, that mass usually how much it may be, means whether equal to the theoretical mass or less than the theoretical mass or greater than the theoretical mass. Like that, if I ask, usually what we will say, equal to the theoretical mass. In the first case, what we did with that equally this mass comes like that, we will expect. But instead of that, it gives a different result, students. Individually, if you are weighing, suppose masses in this nuclear physics are expressed in atomic mass units. Atomic mass units. In the next class, I will explain about this. Suppose, for example, 4 AMU if it results. For example, 4 AMUs if it results. Here also we will expect 4 AMUs, but it comes like as a whole. If you are doing experiment, it comes like 3.9 AMUs. So what is this? Why is this difference, and where it is going? For that we will question ourselves. Individually, if you are weighing, how much it is getting? 4 AMUs individually. Means this is a theoretical value. Okay. Experimentally, what we are getting is 3.9 AMUs we are getting. So 0.1 AMU is the difference. This mass is said to be mass defect, denoted by letter delta M, students. This mass is said to be mass defect. Defect in mass means actually it should result for 4 AMUs. Whenever nucleons are weighed, okay, individually its mass is 4 AMU. But as a whole, if we are weighing, it results only 3.9 AMU. So that difference is said to be mass defect. So for that we can write in this way. How to get for this? one equation we are going to write here now. In what way? You see here. Mass defect can be written as delta M can be written as number of protons into mass of each proton plus number of neutrons means A minus Z into mass of each neutron minus actual mass of the nucleus. This is the actual mass. Here this 3.9 is actual mass of the nucleus as a whole. Actual mass. This is nothing but theoretical mass. Okay, theoretical mass. So that difference is said to be, okay, delta M, which means mass defect. This is nothing but mass defect, right? So likewise, mass defect concept we have, students. Hope you understood for this session, right? We will enjoy with the next session also. Okay, thank you for watching this. Okay, thank you all.